So before we proceed further, let's quickly recapitulate what we did in the last sessions and what is planned for today. In previous two sessions, we discussed extensively about understanding user requirement, we'll discuss about user requirements, we'll discuss about understanding business process, and we also discuss about identify dimension and facts, one of the important concepts. Today we'll talk about why and how to design semantic layer. On top of that, once you identify your dimension and fact, the next step is to identify and create building semantic layer. So whichever tool you use, whatever BI tool you use, you need to prepare a semantic layer. Semantic layer in OBI called RPD. In SAP Business Object we call universe. In Cognos we call, I have exposure to these three products, so I can only talk about these three, but almost all BI products have a semantic layer. So why do we need the semantic layer and what does it add value? So by creating semantic layer, we're going to remodel our existing data model as per our reporting need. The way data model comes to me may not be appropriate for reporting purpose. Let's see scenario. There's a broader overview of the semantic layer. Let's understand this step by step. The first layer is called your disparate data sources. When you build your BI solution, data source could be ERP, could be coming from production system, sales, or different departments. It could be structure, semi-structure and all. Then your ETL team work to extract data from disparate sources and put into enterprise warehouse. In addition to this, they also prepare business data dictionary. That's what we discussed yesterday, business metadata. On top of business metadata, we need to prepare a semantic layer we call universe data access layer. You see the word universal. A universal, it means although you may have multiple data sources, but to the customer it should look as if there's a one data source. And final layer is presentation layer. Right? So the first and most important activity of semantic layer is to give a uniform view, simplify view to my business users, so that it looks to them as if data coming from a single source. I show you an example of semantic layer in OBI. We do have a semantic layer in all BI product. So all BI product generally reorganize your metadata in a way that how business think about it. The first layer is called physical layer. People may call physical layer actual data source. The name could be anything, but eventually it represents your underlying physical data source. In this example, you see clearly my data sources are from different, data is coming from different sources. My some data coming from Oracle, the one which you see, it is coming from Oracle. Another data coming from multi-dimensional database. There's a product from Oracle family called Space. Some data coming from SAP BW, some data coming from flat file. Data, there are multiple data sources, but to the business users, it appears as if it's a single data source. Right? I show you this thing live before we proceed further. So you do not directly query on top of physical source because this is not feasible, not appropriate for reporting purpose. We need to prepare semantic layer. Semantic layer, a generic term used called business model mapping layer, dimension layer. Different terms are used, but eventually it is called business model and semantic layer. And then it's your presentation layer. So I've got three layers. For business user view, semantic layer and physical layer. What semantic layer add value? Let's see from end user point of view. So I'll take a requirement over here. My requirement is like this. I like to see top 5 products, but the difficulty over here, the data coming from two different sources. My data comes from Oracle and it comes from text file, right? But for my end user or business user, I cannot go back and tell them pull data from two different sources. We want to give them uniform view. They should feel as if data coming from single source, right? So all the complexity, the two source, when I give it to my user, it should appear to them as if it's coming from single source. To the user, it's a uniform view, one view of disparate data source. Let's see this live. I am giving an example in OBI, but the concept remains same across any product you use in BI, any industry standard product. Let's take a simple example. Don't fall into technical aspect of it. I want to create top 5 products, top products. As a user, whatever information I need, I drag and drop. So I need product, product sales, and product ranking. Okay. So different tool use different method. Here I apply simple rank function. Say I need product rank. The important point over here to pay attention, my source is RDBMS, Oracle. So I can very nicely see my data is, I can see top products. Right? These are top products based on the rank. Data is coming from RDBMS. So when any BI reporting tool communicates to RDBMS, they use a SQL language. I can see behind the screen what is happening. Behind the screen, the BI product has issued a query. This is my physical query based upon my selection. You can see this is your query, a query rendered by your tool. The query rendered or created exactly as per your physical layer, right? And you see a column table name. These are actual tables. These are the physical tables, your fact tables and all. These are tables, facts and dimension. In this query, the tables are, let me highlight. I use a table called product and revenue. So I have a product table over here, product, and then I would have one table for revenue. So moral of the story, whenever you use any reporting tool, because my source was RDBMS, so the form of source communication was SQL query. It submit my data to physical query, physical data source. But physical data source is pretty complicated for the user to communicate directly. It's very complicated. If you look at the view of it, it is very difficult for someone to understand. Look at the data source. It's pretty complicated to directly understand and query. Let's take a second part of this example. In first part, I pull data from Oracle. In second part, I pull data from non-Oracle source. Any flat file. I use in this example text file. As a user, I don't care whether it is text file, as a database or whatsoever. I don't care about it. My solution should be smart enough to hide this complexity. So now in this example, my source is a flat file. It's a simple text file. But my query remains same. I process it and I find some output. I'll sort them. It is my output, right? Top 5 product. Now let's see how your reporting tool communicates to a data source. Because my source is flat file or text file, my database has rendered XML expression. You would see because my text file cannot understand SQL query, so it render XML expression. So in case your source is non-RDBMS, the source was text file, so the expression, the communication method was XML. So this complexity is handled by your logical data model. This is the simplest example. I could also create one query where I can stitch this data. I can join Oracle data with text file and give a single view to my customer as if it looks to them data coming from single source. This term is called data federation. It is also possible. So why do we need semantic layer? To simplify complexities exist in your underlying data source, which may in terms of multiple data sources, which may in terms of complexity in data understanding and navigation, we hide it. Let's get into more detail and see. Why do we design semantic layer? Semantic layer is designed to bringing only meaningful data to the business user. Only meaningful data. Right? Now imagine you have a column called prod ID. It's a product ID, or product ID, or let's say more complicated column called product abbreviation ID, or something complicated IDs. Now these IDs are not relevant for my end users. They need data in a meaningful format. Right? If I ask you to pick up the product by product ID as a customer, you cannot pick up, right? When you go to Walmart, you can't identify product by product ID. As a customer, you identify product by the name, by the color, or the properties. Similarly, we would like to hide those columns which are not relevant for my user and should be simple, meaningful way. If you look at my presentation view of my data, we have only meaningful information is presenting over here. The way information is organized, it's simple business vocabulary, no complex keywords, column, underscore, all these things are not there. So we hide the complexity. Also, all business logics are handled over here. We're bringing only meaningful data to the user. I have taken two examples. In one example, imagine I have a table called TBL product history. A table product history, it has got 200,000 records. Total records are very high. Because this is a history table and which maintain 10 years of data. And some of my data is not meaningful to me in these days for any kind of analysis. So we would like to filter all the records or bring only those records which make sense for my business intelligence solution. In the simplest example, we say we have a column called product status. Product status say which product is active or alive and which product is retired. I don't need to pull retired products because these are not used for my any kind of analysis. I don't need them. And therefore, when you design your semantic layer, you filter records which are not meaningful for your analysis. Another example over here, there are so many promotion. I have a column table called promotions. There are 100 promotion categories. And 20 years back, we used to use flyers or pamphlets. But these days, nobody uses pamphlets. People use the latest communication mechanism called internet, Facebook and all. So my promotion table is very huge and I want to filter only the meaningful records for my analysis. So I can apply filter. So data can be filtered considering your user needs. Another interesting example. For a Walmart, they have a customer in their CRM solution, customer relationship management solution. They have some table which has got close to 5 billion records. 5 billion records. They're so huge, but I cannot directly do any kind of business intelligence on 5 billion records, and 95% records are not meaningful, not used, may not be relevant for my current BI needs. So they put a filter and say, I like to pull only those customer whose customer I want to do analysis, or I like to do customer survey only for those customers who are my recent visitors. So I have one column called customer last visit date should be greater than current date minus 3 months. This is a logical expression. We wanted only those customer details who visited to my shop in last 3 months. So all this filtering, logical filtering of your data, which may not be relevant for BI reporting, we handle at semantic layer. The semantic layer is business model over here in OBI. All the calculation we put over here. User will communicate to this. All the calculation, data presentation, hierarchy, everything we do over here. Next big activity we do, we implement business logics. Business logic is pretty vast term. A business logic applies in every day in our life. When you apply for a credit card, the business logic apply. There are different kind of credit card, gold, platinum, silver and all, right? When you apply for a credit card, they look various parameters. They look your income statement, they look at your your last 3 months bank statement, your salary statement, your assets, your liabilities, and according to all these parameters, a credit card is assigned to you. Similarly, when you apply for home loan, a business logic apply. So all these business logics may not be available in your source system, which you need to impose on top of that. So another example I've used, all kind of business logic we use a semantic layer. Identify customer buying pattern, because in the last session we are going to talk about implementing retail analysis. So I want to identify customer buying pattern. Customer buying pattern is based on this. This is the requirement given to me from business design document. Identify customer visit pattern. If the average difference between two visit dates is 10 to 30, if the customer visit between 10 days to 30 days, we call the customer as a frequent visitor. If customer visit date is between 30 to 60 days, we call moderate. Otherwise, customer visit is low. So we categorize customer in 3 categories according to the visit date. Another example for product discounting policy. Company has a product discounting policy. If some products are lying in a stock for many days, we would like to come ahead and provide some discount. So product current stock availability and stock in hand, if the variance between both is greater than 100, I've got plenty of stocks available in my stock, plenty of products available in my stock, I like to apply discount. It could be simple, it could be very complicated business logic, depends upon business to business. All these business logics are imposed in your semantic layer. Therefore your semantic layer is designed primarily for. Let's get into more detail step by step. These are 2 simple business oriented examples. Let's talk about complexities at technical front. There are more complexity at technical front as well. The first, the data come to me from my enterprise warehouse is often very detailed, and query on top of that may take ages. When you design your BI solution, if it is not fast enough, nobody like to use it. So one important parameter which you pay attention right from first day, your reporting should be fast, especially at design time. 80% of performance is determined through design time. 20% you achieve at different parameters, at different stages. So first, it's highly recommended to implement aggregate tables. Okay. Now, when data comes to me from my transactional system, this is the hierarchy. Here, well, I show you Excel sheet which make it easy for you to understand. I show you some piece of my data. Okay. Now I have cut the piece of the sample data which is my job. So for the sake of simplicity, I have taken a time dimension. So in Walmart, we are capturing transaction in every minute. That is minute-wise transaction. But this piece of data is not meaningful for any analysis in the same pattern. So what we do, we would like to aggregate this. Aggregation overall purpose to speed up query performance. See, as a business user, it makes no sense to me to look at every minute transaction happening. This is not bringing any information to me. So I like to summarize this. Summarized daily transaction, I summarize to weekly transaction. So previously my hierarchy was year, quarter, I design over here. It was year, quarter, month, weeks and days. And then we summarize and decide to let's hold the data for weekly. So we look at the integration of sales. It's a yearly sales, quarterly sales, monthly sales, weekly sales and daily sales. So if I want weekly sales, I would aggregate the data. Aggregate means sum. All daily sales data would roll up to weekly sales. It further roll up to monthly sales, isn't it? So this data, what you see, is aggregated or consolidated or summarized on with respect to time dimension. What happened behind the screen, when you look at the aggregate data, your database, in case you are using RDBMS, it performs runtime aggregation or grouping. Now imagine in one day I've got 100,000 transactions. Right? In one day there are 100,000 transactions. In 1 week, how many transactions you have? 100,000 into 7. These many rows. In 1 month, nevertheless to say, multiply by 30. The moral of the story, the more transaction I have, more data I have, more time it required to consolidate. So how do I consolidate? Basically it's all runtime. Select sum of sales. In case I'm doing weekly consolidation, year, quarter, month, weeks and days. Right? I want up to week level consolidation, year, quarter, month and weeks from blah 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 table, and I do group by on year, quarter, month and weeks. So this is aggregate at week level. When I want aggregate and monthly, my query will remain same. Only group by will change. From week it will become month. This is monthly sales. When I want quarterly sales, I would aggregate on quarter. So aggregation is runtime and it's very time consuming query. The more data you have, the more time it takes. This is your quarterly consolidation. So this is your pre-aggregated table. This is month level aggregation, this is quarter aggregation, and this is year aggregation. So what we want pre-aggregation to speed up the query performance. Rather than we calculate on the fly, we pre-aggregate. What pre-aggregate tables? The data whatever you wanted, it aggregate beforehand. It's as simple as this. If I want pre-aggregated, I'll take this query and write this statement: create table aggregate at weeks. As that's it, your aggregate table is ready. So whatever data you want, you quickly get it without processing on the fly. Data would be pre-calculated. If you want month level aggregation, it's as simple as this: create table name aggregate at month as the month level aggregation, isn't it? So this aggregation, one technique you should use in your semantic layer. and overall purpose, it will speed up your query performance. You can create a view for logical level aggregation, or you can create a table at your semantic layer. Next thing you can do it, you simplify your model. We prefer to have star schema. Give me 1 minute please. Okay, so the next step, we try to convert our model to a star schema as far as possible. Okay. The purpose of converting into star schema to speed up query performance. The fundamental concept over here, if it is star schema, my query performance would be faster because there would be few joins. Let's take this example. I'll take some data model and write some business query on top of that and look at the cost of the query. This is my query, business model. Let's write up some query on top of that. So my query is simple. My business query says I need a list of products available in stock for last 6 months. List of product available in stock. So I need data from product dimension, list of product. Last, I need data from stores. I need data from time, stock from North America. Let's make this list of products available in stock from North America for last 6 months. I need data from product, stores, time and region. Right. So when I write my query, the cost of query, the fundamental, when you write a query, select query, the cost of query directly depends upon the number of join. So it's like this, the more joins, the slower the query. So the concept we use over here, for example, I need to pull data, so you count a number of join. In this case, your join would be where you apply join with period days, joins with time dimension, period days dot day key, they join on day key, join with sales fact dot day key. Right, and you continue to this and stores dot store key join with sales fact dot store key. So every query, whatever query you write, will have how many joins? 1, 2, 3 and 4. There would be 4 joins. Dot product key with sales fact dot product key, and final join would be with your store and region based on store key. So it would be stores dot store key equals to regions dot store key, region key, okay, store key. This is how they join, or region key. The number of joins are, total joins equals to 4. When I denormalize it, denormalize is simple joining these two dimensions to a single dimension. Denormalization is fundamental concept of database design. So simplest way, you drag and drop and convert them to a single dimension. Now your number of joins reduced to 3, total joins 4, and when I convert to star schema, it becomes 3. When joins are reduced, query performance will increase automatically. So next important step, you to, if possible and as far as it is possible, convert your snowflake model to star schema. Sometimes it may not be directly possible. When you work in the model which I given you is pretty straightforward and simple model. You can simple join denormalize table to normalize them, normalize table to denormalize it. But there are sometimes the model is even little more complicated, which cannot directly be converted to a star schema. Let's take another example. I'll take example with two fact table. In this data model, we have two fact tables. Fact table sales, I add another fact table. Called cost. I have got two fact tables, and hence my model become really complicated. And number of join would be really high. This become my model, and I need to query on top of this model. The cost of my query would be very, very high when I query directly. Why? Because if I write a simple query, I need data from fact cost, some query which need data from fact cost and fact sales. There are more than one way to join them. There are more than one way. And the same query will process multiple times to evaluate the cost of the query. See this? So I'll draw a diagram and say, in this case, in case I want to process my data from cost and sales, I need to pull data from these two fact tables. Right? What are possible ways? Path 1 via, this is path 1. One way I can process my query. This is path 2. This is path 3. Same query can be processed by multiple paths. This is path 1 via dim product. I join fact cost and fact sales via dim product. Second path will be via dim time or time dimension, and third part via channel. When the query has more than one path to process, some database, some BI reporting tool choose the best path, optimized path. I assume out of these three paths, most optimized path is 1. This is I assume. Okay. Your database tool, your reporting tool has chosen path 1 as a most optimum path to process. Some BI reporting tool join them, use a coalesce statement. Coalesce is like a Cartesian producting does. It join using 3. In both the way, the data which you get is not correct. So we use a term called confirmed dimension. A dimension, these three are confirmed dimension, a term come, a dimension which join, which appears between two fact table. A dimension joins between two fact table is called confirmed dimension. In our case, there are 3 confirmed dimension. It shouldn't be the right case, right? So we should remodel in a way that we identify right confirmed dimension. There are multiple confirmed dimension. Therefore, it's not appropriate. So I assume functionally out of 3, Time is confirmed dimension. What would be exactly? We need to go back and look into our business data. So I find my time dimension is confirmed dimension. So every time I process data between these two fact tables, the data would be processed via time dimension essentially, because there is only one dimension. Confirmed dimension is used to join two disparate model. For example, another part of the confirmed dimension, my customer asked me to design a sales and analytics solution. They have got a limited funding, so I designed sales analytics with, I have used one fact table called fact sales. And later on my client says, I'm happy with sales analytics solution, I want to enhance promotional analytics on top of that. I want promotional analytics. My customer doesn't give me complete money and say implement sales analytics, implement, if I like it I'll go further. Next my client says I want to implement promotional analytics. So I've got another fact table called fact promotions, which talk about how much money we invest in different promotions and cost, promotion expenses. So I have got one star schema like this, which talk about sales analytics. I may have another table. Let's take an example for advertisement cost. I've got one fact table which talk about different expenses pertaining to advertisement, right? So whenever you want to join two disparate model, you need a confirmed dimension. So in this way we say I can see expenses associated for different advertisement with respect to time dimension. Similarly, I can see expenses or revenue associated with different sales associated with respect to time dimension. Time is a common dimension when I process data. So you can keep taking multiple star schema and keep joining them using confirmed dimension. From an implementation point of view, confirmed dimension help you to implement incremental solution. Today we design sales analytics, tomorrow I may be using advertisement analytics, like to evaluate how much cost we are paying for each advertisement and how it is increasing my sales. And tomorrow you want promotion analytics, you want different analytics, you keep adding them by using a common dimension. So this is one of the critical thing. Technically it's pretty easy, but functional point of view it's very difficult because business data has to be validated. Every time you write, naturally data would be processed in a different way. When data is processed by a different table, there will be completely different meaning. So let's imagine a case. If my query is processing via time dimension, it's a different meaning. When query is processing via product dimension, it's a different meaning. I write a one-line statement. Fact joins to cost using dim time. And fact sales, right? So these two dimensions joining using time dimension. So I can, in simple English language, I can say I can see time based cost and sales analytics. Whereas if I join based on product, my confirmed dimension, let's make it product, dim products. So it's talking about product based analytics. The functional meaning is completely changed, and the data which you pull from system will also change. So it's one difficult job to identify right confirmed dimension. So the model could be more complicated, the one which I said. You may have two fact table, cost and advertisement cost. This kind of model called galaxy model. There are multiple fact tables. I'm going to split the galaxy model into subject specific analysis. Subject specific analysis. What it mean in this case? See, this is my galaxy model, right? I logically split into two pieces. First, the one which I marked with the red color is my sales analytics, because I have got common dimension called sales, common fact table called sales. This is sales analytics. When my customer want all the expenses, expense analytics or advertisement analytics. I'll use another factor advertisement, and common dimension is time over here. When I take these two, one dimension and one fact, in this example, this is advertisement analytics. Advertisement analytics. When I take fact table, so you split this model into different pieces, and each piece would be subject specific analytics. So in a large big enterprise, your whole model is very complicated, and you split into pieces to make sense as per user requirement. You see this, your physical model is pretty complicated, very huge. What I do in a semantic layer, I simplify them step by step. In a business model, I simplify them in a steps, right? What simplification? Maybe I can highlight and show you. I have some analysis pertaining to customer analytics, which has information related to customer. One part I would talk about for product analytics. One may be represent to sales analytics. So I logically split this into multiple pieces. So convert your Galaxy model into star schema. Next important thing, there is no analysis in the world without time dimension. So you ought to add a time dimension. And time dimension is typical year, quarter, month. You have calendar, you have fiscal. The complexity occurs when you need time dimension at different granularity. See, so when you design time dimension, one thing you design, you need a calendar year, right? Calendar year, you have a fiscal year or financial, right? In general, there is a predefined procedure available which populate your time dimension. You don't have to reinvent the wheel. So typical members of time dimension are your year, quarter, month, week, days, first day of the month, first day of the week, first day of the day, year, right? Days in a month, day of the year. Typical your time dimension is like this, right? And there are predefined procedure available to populate them. The complexity occur when you need time dimension, different level of granularity. So some customer says customer requirements. Some customer says they need detailed analysis. They need daily, hourly sales. Some of my low-end users say hourly sales. Some of my business analysts need data monthly sales, right? But my financial controller and the group of them, they need data for quarterly and half year and yearly sales. So different users have a different requirement. So often the philosophy follow yearly, because they do quarterly closing, half year closing, yearly closing. So often we create multiple instances of time dimension with different level of granularity. Look at this. This is my one time dimension, and the granularity is, or the detailed information this has, daily sales. Most granular data is day ID, calendar date. Most granular data, day level. And second level is month. I have another time dimension, but the most granular element over here, member, is month, fiscal month, and you're capturing sales or revenue for month-wise revenue. Next level of granularity, you maintain 3 tables for quarter. So when you join them, dimension fact, they should be joined on same granularity, otherwise it render or produce spurious data, duplicate values. So this is a common practice being followed in industry. You create multiple time dimension at different level of granularity, and the structure of time dimension would be ideally same: year, quarter, month, first day of the month, first day of the year, number of days in a year, is a leap year or not, and all. That's time dimension. Recognition and ordering is important. Now you see in your business model, in a physical source there are 3 time dimension, right? But I can't show this 3 time dimension to my business user. It's pretty complicated for them to understand. So we have only 1 time dimension. Physical there are 3, but for the business users or analyst only 1 time dimension. And for me as a user, end user, whatever data I want, time dimension is pretty straightforward. I've got calendar and fiscal. Calendar hierarchy is year, quarter, month. Fiscal hierarchy is also year, quarter, month. It only starts from in this fiscal time and day. Fiscal time hierarchy starts from April, calendar starts from January. That may be the only difference. And it may be hierarchy in nature, year, quarter, month, like this. For any BI tool you use, you find the same behavior. The little difference in look and feel only. So simplifying time dimension in your logical layer, next step. Next activity is sometime it occur, not always. That's called many-to-many relationship. Many-to-many relationship is a very nice concept. It is handled through a concept called factless fact table, and we call bridge table. Many people, many times you hear this word factless fact. It seems pretty complicated. I'll give you a very simplest example of it. So let's see this case. Okay. I have one table called salesperson, and another table over here called business deal. Salesperson and business deal, right? The concept over here, we got salesperson number, salesperson ID, and salesperson name. Similarly, I have got business deal ID and deal name, and deal amount, how much revenue we get from the deal. Now problem over here, when they join, the cardinality is many to many. It means one salesperson 101, John has done 2 deal. John was involved in 2 deal. I add a deal ID also over here. Salesperson, okay, and John has done 2 deal 101 and deal 102. John was involved in 2 deal, and therefore the cardinality, one salesperson involved in multiple deal. So my cardinality 1 to many. Right? In this case, let's see the other way around. 1 deal done by 2 salesperson. So John has done deal D101 and 102. Whereas there's another deal called deal 101. Deal 101 done by 2 salesperson. I'm just showing you for the sake of your understanding. Deal 101 done by 2 salesperson. So one salesperson done many deal, and 1 deal done by many salesperson. Right, so from 1 to other, it become 1 to many and many to 1. So my model become many to many cardinality, and many to many cardinality it's very difficult to manage. When you have this situation, you need a concept of factless fact table. What you do is split this, you add 1 dimension between. So now you have salesperson. You have simple basic question, how many your question over here and the deal amount 1000 and 2000, right? And this deal 101 done by salesperson John and Carrie. My question is simple. What is the contribution percent of John and Carrie? Both together worked and completed one deal, but it is not essential both of them contributed equally. How much they contributed? So I want to answer this question, but the question cannot be answered with the current structure. So we add one table in between. First, salesperson has only salesperson ID and salesperson name, and my business deal has got business deal ID and amount. So this kind of model required to be split into two pieces, and we use a deal ID, which is primary key over here, and deal amount. Now I add one table over here which is a primary key for both of them as their foreign key. So I would call factless fact, or I could call in this example bridge table. Now bridge table, what it consists of, it has a foreign key for my salesperson ID and it has a deal ID, right? So I've got two salesperson over here, one John and Carrie, and there are two business deal and the deal amount. So one deal, when I look at my bridge table, salesperson 101 has done two deal 101 and deal 102, and deal 101 done by two salesperson 102, salesperson 102. So you read John has done two deal and deal 1 done by two salesperson. Now in this deal done by two salesperson, what is the contribution of each salesperson? I can also add weight factor. So 101 salesperson has contributed 30% and 102 Carrie has contributed 70%. So if I have, now my cardinality is one to many and one to many. This is how we resolve many to many relationship, and this way you don't have a spurious record. And you can also answer, if I have only two column, I don't have any numeric column. If only two column, this become factless fact. If I also add another column called weight factor, this become bridge table. If there is no fact, it is a factless fact. It's become, if you have a fact also in it, this become your bridge table. So I can multiply weight factor with my deal amount to identify contribution percentage, weight factor percent or contribution percent. So these kind of all complexities may not be directly handled in your source system because they do not have very clear vision about what your source system may have. It is required to be handled in your semantic layer. So we discussed some of the very critical parameters which one should know while designing semantic layer in any reporting tool. There are few examples, a few more examples could be there. I have tried to cover one from each category. Now I open for your question.